Hello again. Tonight we're going to talk about another radiation reflection pressure issue involving photons, particles of light, and smoke particles. If you remember a few weeks back, I was talking about vacuum and photons. And during the after discussion, somebody said, well, if you can't create a field of photons, a flux dense enough to affect air molecules, maybe you can smoke, because smoke particles are probably a lot larger than air molecules. And so I said, sure, let me give that a try. Took me a few weeks to get it all up and running, but here we go. So like I said, back at the end of January, I did vacuum and photons. It's on the Broward Astronomy site, and you can pick it up off of Facebook or YouTube. Maybe if we can use photons to push back on molecules in the air, then that can act as a barrier for a spacecraft or a space station, kind of like an airlock. That doesn't work, then maybe it's just a CO2 scrubber that doesn't require any cleaning or replacement. Maybe as a scuba rebreather. So those were all, if it works, we could do that. But given that air molecules are about 1/1000th the size of a photon wavelength, except when you get to X-rays, which would ionize the air molecules. Not going to go there. Maybe someday. So like I said, the air molecules are much smaller than the wavelengths of photons. So there was a problem there. And I couldn't get the LEDs to be any tighter than 2.2 millimeters, very tiny. But that was just kind of the upper limit on the packaging. And I didn't want to create a special surface mount printed circuit board to pack them even tighter. Now, I even thought, well, maybe if I went with really bright single color, monochromatic ones, I could do that. But then they'd have to be continuously on and they get really hot. So I tried the multicolor ones, and internally, they have an unavoidable refresh. So about every 1/30th of a second, they completely turn off and then turn back on again to save electrical power. So I wasn't able to do that for air molecules, but maybe there's another way to do that. Back in the day, I wrote software for operating systems, and one of the devices we interfaced with was a rotating media hard drive, the old washing machine sized IBM Winchester 3330s. They had a stack of 14-inch diameter platters, and each of them had a magnetically hardened coating up top and bottom, and they spun at like 3,600 RPM, and they had a head that would move in and out. And if ever the chamber, because there's a closed cover and you could take the platters out, if ever the chamber had anybody like blow smoke in it, it would destroy the disk drive, because the smoke particles were larger by I think an order of 10, bigger than the gap between the head and the height it flew above the surface of the metal platters, so it would cause a head crash. So I knew, okay, smoke particles are fairly large. Maybe I can use them. I need to generate smoke particles and then see if the smoke particles can be held back by photons, a field of photons, a flux, if you will. So then I said, well, let me think about this. What would I have to build? How would I have to build this? Now, this is not a force field, not an arc or electrical field. It's just light, like in a circular pattern covering an opening. And I need to test this at sea level, not out in space in a vacuum. So I said, well, I need to generate smoke inside of a chamber. And if I can get the smoke into the bottom of the chamber and I make the photon flux on the top opening, will the photon flux stop the smoke from coming out? If the photons are closer to the size of smoke particles, it'll stop the smoke particles. So then I got some more detail on it. A cylinder, and down in the bottom of the cylinder, you have an inlet for smoke plus air going in, and then you'd fill the cylinder with smoke plus air, and to exhaust it, you'd have another outlet, push the air in with smoke, and then it goes out if you want to evacuate it. But now you need lots of photons in there. So you're not just going to put photons on one side, you're going to put photons all the way around, and then the light's going to cross the opening and create a field, a flux of photons. But you need it to be very high density. So how do you make a high density flux of photons? Well, not with just one ring of LEDs. You need like multiple rings of LEDs, and the light from them will shine 360 degrees around for multiple layers. and then you'd have the smoke in the chamber. If you turn the lights on, then it's not going to come out, supposedly. Here's my smoke generator. It's an incense burner, but I put a cap on the top of it, and I drilled a little hole through the cap for air line to come out, and I drilled a little hole in the top just big enough to let the incense rod go down into the chamber, and then it burns from the bottom up, and the ash falls onto the bottom of the glass cylinder. I had to actually learn how to drill a hole through glass in order to get the hose in the bottom so I could pump the air in to get the smoke plus air to go out the top. Smoke rises because it's hot. And I thought I had to put a check valve in there to prevent the smoke from coming up and going back into the little fish aquarium air pump I was using to pump the air in. That was apparently too much for it, so I had to take the check valve out. But I had little valves in there so I could shut off the smoke leaving and it would fill up the chamber. The problem was it filled it up too well and actually pushed the lid up a little bit and the smoke started pouring out, so I had to seal the top. So here's the actual test chamber. So the smoke chamber and the test chamber. The test chamber has the smoke coming in the bottom, and then there's a valve where I can let the smoke out if I want to. It's like an electronic circuit. You don't want to let all the smoke out. And up in the top, there would be multiple rings in a spiral of LEDs. And so I actually 3D printed a cylinder and then two rims, one for the top and one for the bottom. I used double face foam tape like you use for outdoor lettering attachment. I put that on the inside ring, and then I very precisely manually laid out the LED strip in a spiral up the inside for the width of the double face foam tape. And then I glued the top and bottom rims on there to kind of like contain the light all the way around. There's a picture on the left of what the LED strips looks like. And if you look at it, there's a gap between each of the LEDs. And the way that I covered the gap was this spiral incline inside the test chamber. I offset it so that the row above has, you can see where the LEDs are gapped. And then the row below it is spiraled down from there at such an angle that it fills in the gap. Not perfect, it's not completely tight, but it's better than if I just left the strip with a big gap between them. So the individual red, green, blue LED chips look like this, highly magnified. They're only 2 millimeters by 2 millimeters. And then you see a microscope picture of one. And the area, the 2 by 2 millimeters, is the thing you see in the bottom right picture. The LEDs, the individual LED chips for red, green, and blue, are the things down at the bottom. You see little 3 wires going to the chips. And you'll see that the red is small, the green is big, and the blue is small. And that has to do with the wavelengths of what's being emitted. The red one is actually pure red because you can make a pure red LED. The green one is actually infrared with a sapphire chip on top of it to act as a uplift wavelength converter. Kind of like how a green laser pointer is not really green, it's actually infrared. And then there's one of these little sapphire chips in it that converts the infrared photons to green ones. And then the blue one, that's the modern day like Blu-ray laser player kind of blue chips. If you measured it in the microscope, it would actually be slightly smaller than the red one. But that's just one of those chips, and you can see they're offset. So I had to calculate what distance do I have between them, how much is coming out of them at what wavelength ranges, and how often could I change them and such. Picture on the left is with the flux generator running. It's not a flux capacitor, it's a flux generator running at the full 12 volts. And it was so bright, my mobile phone camera could not make out the individual LEDs. It was just glowing white blob. So I had to drop the power supply voltage down to 6 volts until it was dim enough that you could see the individual LEDs. And you see there's a wire coming in from the top, and then it goes around and around and around and around 7 times around the inside of the cylinder. And they're offset so that the light coming out at a 60-degree angle from each chip was meant to cover the gap. But it doesn't cover the gap quite well enough because there's an area. If you think of it as individual LED as a dome, and then there's a side around the dome, and that's going to have a gap. At the full 12 volts, at full wattage, the flux generator gets warm. Not enough to melt the plastic, so I don't leave it on too long, but it's very bright. I like to refer to it as my own little arc reactor. So here's how I had to create the offset collar, and I had to calculate the dimensions and how many photons per second is coming out of the entire array. And it turns out that this collar with these 320 RGB LEDs at full output produces 1.2195 times 10 to the plus 19 photons per square millimeter per second. But how dense is that? It's just a mathematical calculation. It is what it is. I didn't calculate it as wattage because the entire strip of LEDs is 5 watts, but it's 5 watts in a very small space. So how do I control the LEDs? Well, I use my good old friend, a Raspberry Pi Zero 2W, and I use the pulse width modulation hardware along with a direct memory access channel to just spit out the values. It has a large array of memory that you put the values into, and then you say, send that out there, and it sends it out as individual channel values. But that's, if you ever want to repeat this, there's the secret sauce of how the hardware is hooked up to the Raspberry Pi. Now, if you want to know how it sends the data out, it sends the data out as green, red, blue. So if you think of the data being slid out sideways on a serial communication line, you'd think it hits blue, red, green, but it takes it all in, takes the 24 bits off the front and says, that's for my local LED channels. It strips that off and then sends the rest of it down the serial line to the next LED in a row. So it actually processes it as green, red, blue, and then 8 bits of each. Now, this is how you daisy chain the individual LEDs together. The computer is on the left just before D1, and you have the data that goes into pixel number 1. It gets stripped off, processed, and sent on as all the LEDs minus the first one. And it just repeats that up the spiral line. Now, this slide is only for people that actually try and attempt to replicate this. The hassles I had to go through to get the low-level chip driver working on the latest version of Raspberry Pi OS, which is called Trixie, funny name for that. It was tricky to get it working, and on the Raspberry Pi Zero 2W hardware to do it in hardware using pulse width modulation and a direct memory access channel. There's a lot of minutiae here, but there's the stack of layers at the bottom there. I'm running a script. It talks to a Python module, which talks to a C runtime module, specifically for Raspberry Pi OS version of Linux, running on an ARM version 8 processor at 64 bits. And then it goes out on pulse width modulation channel 0, DMA channel 10. And that's how it does it. But because we're reusing one of the DMA channels and the pulse width modulation, you have to disable the composite audio on the Raspberry Pi. But that's not for regular people. Here it is. People want pictures. People want proof. So I set up another laboratory bench in my house. I'm running out of space. So I set this one up in my garage on a folding table right next to the air conditioning unit. And you can see there's a power strip with a bunch of things plugged in. There's a keyboard and a display, and there's a mouse with a red bottom on it. And then there's some other stuff. The red display is a bench power supply, which are notorious for being inaccurate. So I wanted to get exactly 12 volts out. So I hooked up my little red digital multimeter there and set it to volts. And then I adjusted the power supply output until it became exactly 12 volts. The power supply said, I'm cooking 12.3 volts at 448 milliamps, which turned out to be 4.4 watts. And I went, how come I'm not getting the whole 5 watts? It's because my cheapy power supply maximum output is 5 watts. Not really 5 watts. It got to 4.48. And if I cranked it any higher, it would shut itself down. So I've got on order for delivery tomorrow a 10 amp, 12 volt regulated power supply. That bright white you see in the center, it'll get even brighter by 15%. So here's a close-up of just the core of the test rig, showing all the various parts and pieces with labels. And you can see my arc reactor, my photon flux there in the center. And on the left, you see the smoke generator. No smoke yet. We have some further pictures, but no smoke yet. This is before I started doing anything. And I'm using a inexpensive fish aquarium air pump to pump air into the smoke chamber to push the smoke out into the test chamber. So this is how I observe it. There's a diagram on the right. Air pump goes into the smoke generator, comes out, goes into the test chamber, and then comes out the top. And then there's the sequence of steps I use to prove out how's it working. Here's my results. Hey, the smoke chamber works. You see on the left, it's smoky on the inside. And it's kind of hard to see, but down near the bottom, you'll see a little white area on the incense stick because it's burning. And there's no smoke coming out the top, but the plastic tube, which is normally kind of a milky clear, is white because it's got smoke going out of it. The air pump is coming in from the bottom, blowing the smoke out the top into the test chamber. And with the LEDs turned off, that's the second picture where it says LEDs off, you can see this sort of gray in the image. This is actually an infrared camera shot of the smoke particles coming out of the test chamber with the LEDs off. And it can see the smoke particles when they're very difficult to see visually because the smoke particles are hotter than the air, and they run. So I turned the LEDs on, and I apologize for holding the camera upside down. So it was doing a temperature reading. That's the red text. It's not in some weird language. It's actually 29.3 degrees centigrade or Celsius, sorry. And if you look towards the right in that image, you can see some white stuff going up there, but it's not as dense as the picture on the left. And then the picture all the way on the right is the infrared camera looking down into the test chamber. And you can see towards the upper right, there's that foggy area. That was smoke inside the test chamber with the top open and the lights on. The lights are on. That's that big bright ring you see around the outside. So it was containing some of the smoke particles, but not all of them. So in summary, if I wanted to use a photon flux to act as a barrier to air molecules, unlikely to do that unless somebody built some special parts. Smoke particles being very much larger, I built a rig to try and test that, used an infrared camera, and I thought, I've got to be able to see this. Well, it turns out it did reduce the amount of smoke coming out, but it wasn't completely zero. So I think some of the smoke went up around between the LEDs and came out. And if you don't think photons can move things, there's a 2018 Nobel Prize in Physics for you to read. They used a 5 milliwatt infrared laser to actually push bacteria around under an X-ray microscope. And that was only 5/1000th of a watt. But that was a laser. These are not lasers. These are just very bright LEDs. Can I do any better? I'm only using a 6 watt. They do make not just RGB, but RGBW, 4 LED chips, one of which is bright white, and you can turn them all on at once. So that would produce more white light. Maybe it would constrain things more. If I wanted to avoid the smoke getting out the spiral, I could make 2 of those cylinders, one wrapped this way and one wrapped this way, that would confine the smoke. And I do have on order a higher power supply that instead of getting me close to the 5 watt limit of the strip, it would pump in 6 watts, which would be at the peak of the strip and give me a full 5 watts or about 15% brighter white, more photons than it does now. I'd also prefer LEDs that didn't internally refresh at 30 times a second. They're turning off and on 30 times a second to save power. And if that means that I can't send data to them fast enough, I'm fine with that. Somebody out there, do better than I did. And then all the links as usual. Comments, questions?
That's cool, Monroe. I think it was me that asked about that. I was thinking about like a smoking room being blocked off, let's say in the Hard Rock.
Yeah.
Or someplace, and using light to do that. What about instead of LEDs, what about a rapidly sweeping laser beam? I'm not sure how rapid it would have to be sweeping, though.
Well, if there's smoke particles leaking out because the LEDs are being refreshed, turned off and on 30 times a second, and the smoke is leaking out, then I think you'd need a continuous laser beam. I don't think sweeping it would wherever the beam is, it would affect those smoke particles. But wherever the beam isn't right now, the smoke would
Yeah.
go through. So
Well, I don't know how fast you can get a laser beam to sweep versus the 30 times a second LED.
a couple of hundred times a second, but it's
Mhm.
still going to be a lot of places where the laser isn't, but the human
Yeah,
eye can't perceive it. And
yeah,
we need something that smoke particles can perceive, not human eyes.
yes.
So, if I could make one of these LED strips and I could put the LEDs really close together, then I could probably do this same spiral and seal it off. And I think
Yeah,
the results would be interesting. Or if somebody wants to create a custom printed circuit board and make their own LED array, if they printed it on flexible printed circuit board, they could make a collar and they could put the LED devices right next to one another and then put the next row up in between the gap. And they could make like just 2 rows and you would have photons completely encompassing it and make it with chips that don't need a 30 hertz refresh.
right.
It would require more electrical power to do that. One of the things that I decided was instead of using the normal 5-watt RGB LEDs, I used the not 5-watt, 5-volt RGB LEDs. I use the 12-volt RGB LEDs. And if volts, watts, amps, math, volts are the pressure. If you think of it as a garden hose, if I have a garden hose with more pressure behind it, I get more water out of the garden hose per second. And by changing it from 5-volt to 12-volt, I would get more photons per second. And my calculations, it went from plus 17, times 10 to the plus 17 photons per square millimeter per second to plus 21. So that was a huge boost in the number of photons per second in the flux. But I think that the separation, even though I tried to accommodate that, it still leaked out. But I just think of it as, okay, it maybe cost me 120 bucks, something like that, to set up the entire test rig because I use cheap stuff. Like I said, the smoke generator was an incense burner, and the test chamber was actually a Vita seasoning bottle. Like you get a tall bottle of garlic or parsley or something like that with a screw top lid on it and a little snap-on filter. And I took the filter off, cleaned it out, and then I made my 3D design fit snugly right inside the opening at the top of the bottle and just slid it in there. And then I put tape around the outside of it so it wouldn't leak. And, you buy a kit of fish aquarium parts, the pump, some hose, some valves and tees, and that's your plumbing. And the incense burner came with a bunch of sticks of incense. They were unscented, unflavored
Ah,
because they didn't want to gum things up with any kind of resins or anything. What I did do is I realized that even unflavored, unscented incense has an aroma to it, which is burning punk, like burning bamboo. Because that's all the punk is like sawgrass weeds, ground up and stuck on the outside of bamboo sticks. So yeah, my house was smelling like burning bamboo most of this afternoon. And it sticks to your fingers too. So my hands, until I took a shower this evening, smelled like burning bamboo. That may be why I'm hoarse,
yeah.
is I inhaled the burning bamboo.
Yeah, I've got a question about the LED chips,
Sure.
red, green, blue. Is each chip using the same amount of current?
Yes.
Okay, you don't have to change it for each one.
No. It actually passes it along nicely. Let me show you. Okay. This is one of the chips. It's very much enlarged here, but the picture down in the bottom center, that's actually one of the chips. And they're just on this strip and they're joined together. So the power just goes from one chip to another. The ground goes from one chip to another. And the serial data signal goes in one chip, out into the next chip's in. So it's out, in, out, in, out, in. And you hook them all together in a strip and you apply power to one end. Let me see if I can show. There you go. See this big cable coming into the top of the opening? It's got 3 wires: power, ground, and serial data. And the serial data is generated by the Raspberry Pi computer. Normally, you would like make the LEDs blink and dance and change colors and stuff. I just wanted them god awful bright white. So I just set the R, G, and B, red, green, and blue channels to 255, 255, 255. So maximum output. And it did max. Oh, and you can daisy chain them. It's kind of hard to see, but if you look right down in the bottom here, that little black area, there's actually a connector on the bottom side of the LED strip. So if you wanted to daisy chain another 320 LEDs together, you could. You just need more power. Now, obviously, you're not going to be driving the power for the LEDs from the Raspberry Pi. You need a separate power supply for that. And that's why I was using my bench supply. But my bench supply taps out at 5 amps, and I need 5 amps at least. So I've got a 10 amp dedicated power supply arriving tomorrow. I can swap that in and see if it makes any difference. I don't think it will. I think the smoke is getting out between the LEDs. But they're really great for decoration. And you can get them in long strips with a varying number of LEDs per meter. I chose the denser ones, 144 LEDs per meter. And there's a 2-meter strip there, so 320. You can get them in squares, so you can get them in a matrix, and you can actually put graphics on them, or lettering, or numbering. Very fancy stuff. If you go to adafruit.com, there's all kinds of stuff there, information on how they operate, how to hook them up, how to do the software, all that kinds of stuff's available.
I missed that. What.com?
Adafruit, Adafruit.com. And what you're looking for is Neopixels, Neopixels. They got lots of stuff on them. Now, individually, these LEDs are 18.75 milliamps per chip.
Yeah, I got to keep my mic muted. There's noise from the other room here.
I understand. But when I saw how much white light was coming out of that round circle, I went, oh, it's my own little arc reactor. I feel like Iron Man. But it was surprising that I had to tape seal the top of the incense burner because under pressure, it was leaking out. So I had to tape seal the top of it to get it to push the smoke down the tube. And then it stopped at the check valve. Now, I made sure the check valve was in the correct direction, but the little stone that's inside the check valve, it's actually a rubber plug, was blocking the smoke particles. It wasn't blocking the air, but it was blocking the smoke particles. So I popped that out, used a longer tube, and hooked it up that way.
You'll have to explain all that to the narco cops when they come knocking on your door. You're just making an experiment. There's nothing.
Hey, I'm going to be posting this video publicly on YouTube. So, yeah. And there were no special resins involved. Like I said, unscented, no resin. And I was burning just a pure punk. I am a punk, yes. I was burning just a pure punk incense stick.
Well, you're missing all the fun. You could put some other things in there and smoke that.
There was enough things that were affecting my air and breathing and voice. So, but you got to wonder, if somebody's monitoring my Amazon shipments, it's like, what in the hell is he doing? He's building an arc reactor. Yeah. I just thought it was so cool when the incense burning was burning and you could actually see the smoke filling the chamber and the glow from the burning incense stick at the bottom.
Very cool. So can you see any real world applications for this? I could see scientific applications in a controlled environment, but like in a casino or something like that, if you have people constantly walking through there and air conditioners,
Yes.
It's just too much going on to have just light blocking the smoke.
I think if you made the light just less than ultraviolet A, you would have small enough wavelength to block smoke. And then if you custom made an LED strip that just went kind of in a U shape through a door opening, you could probably block a lot more smoke than is blocked today. Because today they just use reverse air pressure. They literally, the smoke-free part of the casino is the smaller part of the casino, except at Pompano. At Hollywood and at Coconut Creek, the smoke-free area is smaller than the rest of the casino. So all they do is they pump a lot of fresh air in from the outside into the smoke-free zone that pushes the smoke out. And if you had one of these around the opening, then maybe you could save the money on the air pressure and wouldn't have people popping their ears in the smoke area. But I also think that this is fledgling science just waiting for somebody to produce a metamaterial. You know, because if you did a deep violet, not ultraviolet, but deep violet, and you made the LEDs single channel, monochromatic, very bright, and just like with no lens and packed right next to each other, and you made that strip go up and around so you could tape it in to a door opening, I think you could actually block a lot of particulate matter from going through that opening. And given that it was covering the entire area, you could walk through it and the light would go around the outside of you as you pass through it, kind of like, you know, a lower power force field. So I think there's a huge avenue for corporate investment here if they have the willing to do a little testing work. And it won't cost millions of dollars to do it. It might be tens of thousands of dollars to prove it out. But once you did it, it's like, hey, Samsung, want to make billions? Because they would produce the LEDs.
Oh, yeah.
Yeah. So, okay. Any other comments or questions before I stop recording? Hearing nothing.